Today we look at the dot product. Now the dot product has a geometric and a component formula, and we'll look at both of them. But before that, let's look at what the dot product actually is. Now you'll need to get these notes down in your book. Let's read through them. The dot product is a way of multiplying vectors where the solution is a scalar quantity, and that means that it's got magnitude but no direction. Now have a look at this word here. It's a way of multiplying vectors. There is another way. Let's jump down here. It is not the same as taking two vectors and actually multiplying them together completely. That would be called the vector product, and that's something we're not going to do in this course. It actually gives you a solution that is a vector, which sort of makes more sense in a way than this dot product. So the dot product, it's a way of multiplying the vectors, but we're not exactly multiplying everything about the vectors. We're just multiplying their scalar quantities and considering the angles between the vectors. Now it's written this way with the dot. Now the dot is not like a full stop. A full stop generally sits at the bottom, like on the line of your writing, whereas this dot is sort of in the middle between the two vectors. And the dot is generally a little bit bigger than a full stop, so sort of colour in a little circle there when you're writing your dot products. Now the use of this dot reminds us that we're not multiplying everything about the vectors, so we use the dot instead of the multiplication, and it's the dot that gives it its name. Now, because the answer is a scalar quantity, the dot product is sometimes called the scalar product, but we have to be careful that we don't confuse this with multiplying a vector by a scalar. We've already seen how to do that, and we put the scalar out the front of the vector, and that just makes it a certain multiple of the vector. So the geometric formula for the dot product is this. If we have two vectors, now disclaimer here, these vectors have to have the same tail. And if they do, then the dot product will be the length of each vector multiplied together, remembering that the absolute value of the vector is just its length, multiplied by cos of theta, where theta is the non-reflex angle between them. So being non-reflex is important here. So let's consider two possibilities here. If we've got two vectors with the same tail and there's an acute angle between them, then theta will be in here. Clearly it can't be the angle out here because that would be a reflex angle. And if we have an obtuse angle, then theta will be obtuse. That's okay, but it won't be this angle out here because it would be a reflex angle. Okay, now I've written the geometric formula for the dot product at the top of my page here so that we can refer to it as we look at some special conditions that occur. Now you might notice that I've taken the multiplication signs out of it just to get a slightly simpler form. And you'll also see that this formula is on your reference sheet. So it's not one that you need to memorize, but it is one that you need to be able to apply. Now if theta is acute, then the dot product will be positive, whereas if theta is obtuse, the dot product will be negative. Now this makes sense because both of these parts are actually just lengths, so they're always positive. So if cos theta is positive, then the dot product is positive, and vice versa. Now, we know that cos of theta is between 0 and 1 when theta is acute, whereas when theta is in the second quadrant and it's obtuse, we get a negative answer for cos theta. So that explains that quite simply, I think. Parallel vectors, there's two possibilities. Either they have equal direction, they're going the same way, or perhaps they might have opposite direction but still be parallel. Well, if they're going the same way, then we say that the angle that's between them is 0 degrees. And we know that the cos of 0 is 1. So that means that this whole part of the formula becomes 1, and the dot product of parallel vectors going the same way is just going to be their lengths multiplied. Whereas if parallel vectors are going the opposite direction, we say they've got an angle of 180 degrees between them, which I think makes sense. And we know that the cos of 180 is negative 1. So we're going to get just negative 1 for this part, and we'll get the negative version of their lengths multiplied together. Now, equal vectors are really just parallel vectors going the same way that are exactly the same length. So they're identical. So instead of saying we have one multiplied by another and referring to them as, say, vector A and B, they would both be vector A or vector B or vector C, whatever they are. So we really just need to take the length of one of them and then square it. That makes sense, I think. Now, this bottom one, it's at the bottom of the page, but it's potentially one that you're going to use the most. Perpendicular vectors have a 90-degree angle between them, and we know that the cos of 90 degrees is 0. So the dot product is going to equal 0 as soon as that part of the formula equals 0. So if we're getting a dot product of 0, we know there's two possibilities. Either the vectors are perpendicular, that would cause it, or one of these could be the 0 vector, or perhaps both of them. So I guess you could say, or either one of these, or at least one of these is a 0 vector. So we're going to use this quite a lot in the exercise today to prove that two vectors actually are perpendicular, because if their dot product equals 0 and neither of them is a 0 vector, then they must be perpendicular. And now let's look at the laws that apply to the dot products. The commutative law just says, can we do things around the other way and get the same result? And the answer is yes, we can. The associative law says if we're multiplying some scalar quantity by our dot product, what do we do? Well, the dot product, it's not a perfect multiplication of the vectors, but it's a type of multiplying. And we know that if we were multiplying two other numbers, let's just say we had 2 times 3 in brackets and we were multiplying the whole thing by 4, we know that we don't need to do 4 lots of the 2 and 4 lots of the 3. Effectively, we've just got 4 times 2 times 3. And the same thing happens here. You can just put that scalar quantity out the front of your entire dot product. And I think that makes some sense. Another one here is that if you've got each of your vectors multiplied by some scalar, then you can multiply those scalars together and put it out the front, and then multiply that by your dot product. The distributive law says, how do we handle brackets when we've got something added inside the brackets, which is quite different from this one where the thing inside the brackets is multiplied. Well, as you would expect, we can just get A dot B and A dot C and add them together. So this one can save us quite a lot of time if vector B plus vector C doesn't give us anything sensible that we want to work with. We can use this workaround.